The agenda for today, we will talk about the GPU and as an accelerator. You know that GPUs are originally devised for processing graphics. We don't really care about that side of the GPUs in this lecture. We are only going to talk about their capability as general purpose processors. And there, the way that we are going to organize this lecture is by first presenting what's the typical programming structure when we write CUDA or OpenCL programs, which are the way of programming GPUs for general purpose processing. And we will talk about the bulk synchronous programming model, bulk synchronous parallel programming model. What does it mean? What are its limitations? And then we will talk about the memory hierarchy and memory management, and finally some performance considerations, let's say things that we have to take into account when we want to optimize programs for GPUs. This is not usually not trivial optimization, so that's why it's interesting to talk about them. And also they are kind of, even though we are going to be talking in particular about GPUs, they are kind of like generic optimization techniques that you may also use on other platforms as well. Finally, only if we have time, we will start talking about collaborative computing. This is, let's say, like new programming features that allow us to use different devices in a collaborative manner, working on the same workload, let's say application. Okay, recommended readings. The first one is clearly the CUDA programming guide. You will see it's a lot of documents there, from the very basics of CUDA programming to like very complex APIs, functions, and programming tricks. And if you want to read a book, there are several good ones, but the one that I would recommend is this one by Professor Wenmei Hu and David Kirk. The other day, in the last lecture, we had a few more slides to cover about example GPUs, and this is where we are going to start right now. This trend of GPU programming or general purpose programming for GPUs started like around 12, 13 years ago, and the very first architecture was called Tesla architecture. We will talk a little bit more about the different architectures later over the lecture, but this is kind of one of these first GPUs that were capable of doing general purpose processing. In NVIDIA speak, this has 240 stream processors, and this is SIMT execution. Recall that we talked the other day about SIMT execution. We will recall that again today. And in generic speak, these 200 stream processors that NVIDIA also calls CUDA processors are actually 30 cores, 30 GPU cores, or 30 SIMD pipelines, each of them including eight lanes. So you will see the detail. Actually, you can see the detail here. This is one of these cores, one of these streaming multiprocessors in NVIDIA terminology, and inside each of these we have these different lanes. You can see the 8 of them. Inside each of them we might have several processing elements or several ALUs, let's say. For example, we have something that is able to do multiply accumulate operations or multiply add operations that are very useful for linear algebra, for neural networks, for example. And we may also have other ones. We can have special units for integer computation, for floating point computation, and this is also something that has changed a little bit over time in the different designs of the GPU architectures. But essentially, the thing that we have inside one of these GPU cores is what you can see in the slide. So as you might remember as well, on each of these GPU cores, what we execute are, well, what we do is mapping thread blocks. You might remember that term from the previous lecture. And these thread blocks are decomposed into warps. And each warp is a set of 32 threads that are going to run in parallel. They're going to run concurrently as a SIMD unit, as a basic SIMD unit. We will talk a little bit more about this today. And this is like the, let me show you. Okay, no, wait. This is like the full picture of the entire GPU, this GeForce GTX 285. And here you can find the 32 GPU cores that the first slide mentioned. And actually, even though let's say the basic architecture is essentially the same, it has evolved a lot in the last 12 or 10 years, right? This one was released in 2009, but the first CUDA-capable GPUs were released like 2-3 years before. And yeah, but the thing is that in the last 10 years, you can see how much the number of these stream processors and how much, what is more important, how much the peak throughput has increased. I mean, it's more like 30 times, right? So from this GTX 285 until this V100, NVIDIA Volta V100 that was released in 2017 and is especially devised for training deep neural networks, among many other tasks, of course, that you can run on it. And this is the Volta NVIDIA V100. Now observe that how much this number of stream processors has changed from 240 to 5,120. Much powerful thing. The way that they are organized is a little bit different. In the other GPU, we had like 30 cores with 8 SIMD functional units per core, and here what we have is 80 cores with 64 of these CUDA cores or stream processors. Something interesting also in this Volta architecture, something that started actually in this Volta architecture, is some specialized functional units for machine learning. These are called, in NVIDIA terminology, these are called tensor cores. We'll see something more in the next slide. But here, for now, what you can see is the entire block diagram. Each of these rectangles here is one SM or GPU core, and actually is divided, as we will see in the next slide, better, is divided like in 4 different pieces. If you count the number of SMs or the number of GPU cores here, there are 18 total. Observe that they all have access to this shared L2 cache, and from there you can access the memory controllers to the HBM2 memory that provides very high bandwidth, around 800 or 900 gigabytes per second. These are some numbers on the right-hand side about what's the peak throughput that you can get in single precision, double precision, and also for deep learning with these tensor cores that you can find here. Observe that this is the picture of an entire SM or CUDA core. And it's actually divided, like, as you can see, like in 4 different parts, but essentially what we have in each of these parts is the same. We have an L0 instruction cache. From that one, the warp scheduler reads instructions and dispatches instructions for the individual warps onto these different units that we have here. Here we have 8 floating point 64 for double precision computation. Here we have integer units. Here we have floating point 32, and these are these tensor cores. What does exactly mean, these tensor cores? Well, it's something like this. For each of these tensor cores, what we're going to be able to do is kind of this computation. Observe that we have 2 input values, we multiply them, and then we accumulate the partial result with more products coming from other tensor cores. As you can see, this is able to do sort of mixed precision we are not working with floating point, so with single precision or double precision floating point operands, but with half precision. This is 16 bits to represent the floating point number. It is like very common practice in deep neural networks, because with this precision is more than enough to train and to do training and inference in neural networks. And actually you can have what you see here with this mixed precision, because the input operands are 16 bits, but the output are 32 bits, or you can also have the output with 16 bits. And this is more or less like the computation that each of these tensor cores is able to do, essentially multiplying two matrices of 4 times 4 and accumulate with the original values of matrix C. So this is A, B, and C. So by decomposing an entire matrix multiplication into many of these tiles and mapping these tiles onto the tensor cores, you can achieve like very high throughput, as you can see, which is essential these days to train networks fast and in an efficient way. That is why these GPUs are, let's say, like the accelerator of choice for training neural networks, even though there are like other architectures as well that are being designed and are being explored for the same purpose. Actually, this is more or less what this slide is about, this food for thought. What is the main bottleneck in GPU programs? This was something that I wanted to ask you the other day at the end of the lecture, but we didn't have time. Maybe you started figuring out what were the bottlenecks in GPU programs. We are going to talk about this today for sure. About these tensor cores, we are talking about these tensor cores like very useful or very efficient to train deep neural networks to essentially perform matrix multiplications, because as you may know, what we do with when we are training, well, not only in training, also in inference, when we are running neural networks, what we do is mapping the convolutional layers, among other layers, as matrix multiplications, and that's why we can easily map them onto these GPUs and onto these GPU cores and achieve very, very high throughput. And the question here is it possible to use these tensor cores, which are super fast and very nice, is it possible to use them for other applications? Well, this is something that some people are exploring these days, trying to do, and trying to see how to modify slightly these tensor cores in order to be able to do more computation. For example, there is a very recent proposal in Micro 2019 about utilizing these tensor cores to execute sparse matrix computations as well, which is going to be like more and more important for neural network training. Another question that I wanted to ask you is, can you compare and contrast GPUs with other accelerators? In particular, it's very nice to compare them with systolic arrays. Why is that? Because systolic arrays, and as an example of them, TPUs are like one of the other good alternatives for training and inference of neural networks. I think that we might not cover systolic arrays here in this course, but if you're interested, you can watch Professor Mutlu's lecture in Design of Digital Circuits. And you will start figuring out what are the differences, and maybe, at some point, it would be nice to combine both paradigms. Which one is better for machine learning? Try to answer that. Which one is better for image and video processing? In the end, there are a lot of similarities between machine learning or, in particular, deep neural networks and image and video processing. Why is that? Because in the end, we are working on usually two-dimensional or three-dimensional inputs, and the way that we operate on them is by applying filters on top of these inputs. Input feature maps is the name that we use in neural networks, and we will see how we operate on these different tiles when we are doing GPU computing. It's something that we are going to cover in this lecture today. And what type of parallelism each one exploits. You already know what type of parallelism GPUs exploit, right? Recall that we have SIMD, and inside the, it's the SIMD paradigm, they have kind of vector processing, but also array processing. But we also talk about fine-grained multithreading, right? Recall that I had the other day a few slides to talk, introduce briefly fine-grained multithreading. Yeah, these three types of parallelism or these three types of processing paradigms are inside the GPUs. We are going to talk today more about especially the fine-grained multithreading thing. And what are the trade-offs on GPUs? Yeah, everything has trade-offs in life, right? Okay. Yeah, so we're going to talk about these trade-offs for sure. Recall this slide. How is each of these GPU cores or SIMD pipelines composed? Recall that, and this is actually what you have seen in the previous slides. Recall that in each of them, what we have is one stage where we are fetching the instruction. This is what the warp scheduler does when goes to this L0 or L1 instruction cache and reads one instruction and starts decoding it to issue onto the lanes. So we decode it, and then we have this kind of scalar pipelines in parallel, and each of them represents one of the lanes inside one of the SIMD lanes inside the GPU core. We need to go through we need to read from the register file what are the operands of the arithmetic operation, for example, that we're going to execute. And then we have our ALUs, which are these, you have seen these multiply add and multiply units. And then we have a data cache, L1 cache. From this one, if we miss, we will have to go to the L2. And if we also miss there, we will have to go to the global memory. The DRAM essentially is called global memory in GPUs. And and then finally the write back, we will write to the output to the register file. Also recall how one warp is executed on these units. We talk about different possibilities, right, of mapping the computation on the multiple lanes that we have, and it will depend on the number of lanes that we have. Recall vector processors. We might be writing SIMD programs where we assume that we have a certain length of the or SIMD unit. And then, depending on how many functional units we have, we will have to perform the computations in a different manner, right? Based on how many functional units we have. In case that we have one single functional unit, we can have, let's say, concurrency in time. For example, here we have first launched the computation of A0 plus B0 and obtain C0. After that, we input the operands to compute C1, C2, C3, and so on. If we have more of these units, we can have more of these operations in parallel. So we can have concurrency in time and in space. How do these SIMD lanes look? Each of these is going to be one of these SIMD lanes. We may have several of these functional units, and the operands are going to be provided by the register file. The register file has in total a certain size. This is the number of registers that we have inside each of the GPU cores, and what we do when we map the threads onto these GPU cores is that we need to partition this register file and assign each of the threads as many registers as it needs, obviously, as long as we have enough registers for that. And we are also going to talk about that availability of registers and how much it impacts in the overall execution of the warps. And you may also recall this one. This was for an example where the warp size is 32, so we are going to have 32 warps that are going to execute in lockstep. We are going to execute concurrently, but the way that these actually are executed onto the lanes depends on how many lanes do we have, right? So in this example, we have 8 lanes. So if we want to execute 32 threads, what we will have to do is launch 8, 8, 8, 8 up to 32. So in every cycle, we will start running or we'll start executing 8 threads. And this would be like the first instruction. For example, in the load unit for warp 0, we execute a load instruction, and maybe here in the multiply unit, we execute a multiply instruction for warp 1, an addition for warp 2, and again, load unit, warp 3, warp 4, warp 5. This slide, very quickly, just for you to have it as a reference, because as you can see, I'm actually mixing a lot of terminology here, right? I'm talking about the NVIDIA terminology. I could also talk about AMD terminology, and then we have the generic terminology, which is what we would really need to use, but it's also good that you are familiar with the terminology of the different vendors. And yeah, this is, for your reference. So, sir, for example, when I talk about GPU core, is what NVIDIA calls a streaming multiprocessor, or inside a streaming multiprocessor, what we have is what NVIDIA calls streaming processors, and this is for us a SIMD pipeline or SIMD functional unit. Okay, let's start talking about the basics of GPU programming. And the very first thing is to recall this slide that we also presented the other day. What was one of the main drawbacks of SIMD processing? One of the main drawbacks of SIMD processing was that it's difficult to program, right? And this is, this is what somehow with both synchronous parallel programming models like CUDA or OpenCL, we are trying to solve or trying to tackle. This trend of general purpose processing on GPUs, as I said, started like 12, 13 years ago, and the most interesting contribution here is that it's going to be easier, or it's easier to program SIMD processors with the SPMD programming model. We already discussed this SPMD programming model the other day. Yeah, many people say that GPUs have democratized high-performance computing because achieving the throughput, the performance that you can today achieve very easily, even in your laptop, with one of these GPUs is, it was like, very prohibitive. Like 15 years ago, it was something that we probably couldn't only achieve in big clusters and supercomputers, but these days is everyone can do it in commodity PCs even. And they are typically very good for workloads where we have very inherent parallelism. Of course, the good thing of the SPMD programming model is that it is also possible to implement irregular workloads. It's also possible to implement to have divergence across different threads running concurrently. Obviously, the performance is going to be degraded, but it's still possible to program them this way. But they essentially are very, very good wherever we have inherent and regular parallelism. And examples of that are linear algebra, that's why matrices, image or video processing, and deep neural networks. However, this is not for free, and why is that? Because there is a new programming model and we have to learn it. Algorithms need to be re-implemented and rethought. That's the first thing to keep into account, because, if you are used to write C programs, for example, or Fortran or C++, which are essentially sequential computation, obviously you need to find a way of taking advantage of all the threads that you can have running in parallel, right? And that's not so trivial. Good thing is that there are already like many or several higher level programming languages that allow you to express this parallelism in a more easy way, something like OpenACC, which follows kind of similar paradigm as OpenMP. You might be more familiar with OpenMP, right? You have a for loop, and before this for loop, you just write pragma on parallel for, and then the compiler will do the work for you, right? Something like that, for example, exists also for GPUs. It's called OpenACC. And yeah, for sure, you can achieve good performance for very regular workloads if, your program, your computation, your algorithm is a little bit more irregular, then obviously it's going to be more difficult, and it will be better, it will be necessary to go and directly program in CUDA or OpenCL. And and even though GPUs are super powerful, super fast, there are still some bottlenecks. The first bottleneck is the fact that the GPU is an accelerator, right? And it's typically connected to the main system through the PCI Express, or now, for example, NVLink has this fast kind of PCI Express that can achieve a little bit more higher bandwidth, but still is like one order of magnitude slower than accessing memory. And even accessing memory, accessing DRAM from within the GPU cores, it's also a bottleneck. Why is that? Because even though these memories, GDDR5, GDDR6, and HBM2, are, they can provide you something between 300 gigabytes per second and 900 gigabytes per second. This is still far from the peak throughput that you can achieve. And then actually something interesting is recall how I started with this GTX 285 and this Volta V100. If you compare both, if you check what's the peak throughput in teraflops or gigaflops that the original, the first one gives you, I don't remember the exact number, but might be something around 100 gigaflops compared to the 15 teraflops that the V100 provides. So if you compare these two numbers with the memory bandwidth of these two GPUs, you will see that the ratio between them has increased, meaning that now GPUs, so the cores, the number of cores and how powerful these cores are is higher with respect to the available bandwidth than it was 13 years ago. What does it mean? It means that the GPUs are more powerful, they have much more bandwidth, but this bottleneck is even worse 13 years later. Okay, this is something that for sure you know, but it's always good to recall, to remind what's the main difference between a CPU and a GPU. The main difference is how are you using the area that you have in your chip. And a CPU, you know that we typically have few out of order cores, very powerful cores, but only a few of them. A lot of this area, a lot of this die is used for control, for example, doing speculation, branch prediction, and these sort of things. And then we also have like very big caches, right? We have deep cache hierarchies in CPUs. On the GPU, most of the area is devoted to cores, computing cores, typically in order fine-grained multi-threaded cores. What we need to for control for caches is much smaller, and actually this more, let's say, corresponds to something old like this GTX 285, where we didn't even have L2, or we couldn't use it for the general purpose pipeline. Now we actually have an L2, but it's still the size of these caches compared to typical sizes on CPUs is much smaller, significantly smaller. Okay, and this is first slide of how do we compute on the GPU, how do we offload the computation to the GPU. 3 steps. First, we will usually start the computation on the CPU side, where we are going to have the original data structure that we want to operate on, or data structures that we want to operate on. So the first thing to do is to transfer input data from the CPU memory to the GPU memory. Second step, performing the computation or kernel execution or multiple kernel execution. And finally, we will transfer the results back from the GPU memory to the CPU memory. So these are the basic steps, especially in discrete GPUs, which are the most common ones. Any of these laptops and also especially desktop computers, the GPU is discrete, is connected to the PCI Express, in the best case connected to the NVLink. So we will always have to do this thing. These days it's more frequent to find system on chips where we have inside the same chip we have integrated CPU, GPU, and maybe more accelerators, etc. And they have access to the same memory space. By using that, we can enable many more features. And this, if we have time, we will talk about that at the end of the presentation. But still, what's the problem with those GPUs, integrated GPUs, is that they are usually much less powerful than discrete ones. And what's the typical program structure? I talk about traditional program structure because that's the, let's say, what is called sometimes the original accelerator model that follows exactly what I'm explaining here. Discrete GPU, where you have originally have your data in the CPU memory, you need to transfer it over the PCI Express bus to the GPU memory, and then you start the computation. That's a traditional accelerator model, and the program structure for this, it's going to be something like that. I think that you have already seen this slide before. We will start the computation doing some serial code or modestly parallel code on the CPU side, and then we launch a parallel kernel on the GPU. For this kernel, we launch a certain number of thread blocks, and each of these thread blocks contains a certain number of threads. You can see them all here. When they all finish the execution, the kernel terminates, and then the control is returned to the CPU, and then we might launch a second kernel, kernel B in this case. One thing that you can notice in this slide is that 2 terms that we are going to be using interchangeably with CPU and GPU are host and device. When we talk about host, we're talking about the CPU. When we talk about device, we're talking about the GPU. It's better when talking about CUDA programming or talking about OpenCL programming, it's better to talk about device instead of GPU, because in the end, the device could be something different as well. As you may know, with OpenCL, for example, you can also program FPGAs. And actually, I don't think that we will have time, but I have a few slides at the very end of the presentation, because the same role that the GPU can have as the device in CUDA programming, for example, can be applied to an FPGA in OpenCL programming. Okay, so recall this single program, multiple data, or single procedure, multiple data. This is a programming model rather than a computer organization. We were talking the other day about this. We are going to have multiple instruction stream executing the same program, and each program or procedure is working on different data and can execute the different control flow path. We will see how this is done, how we need to write these programs, what are the implications of doing that, what happens if we actually follow different control flow paths, and we will also discuss about how, whenever it's possible, we can try to avoid these different control flow paths, or program them in a way that we can still be more or less efficient. CUDA and OpenCL follow, as I said in the beginning, this bulk synchronous parallel programming model. This essentially means that there is no global synchronization inside the kernel. When I talk about a kernel, I think it's something that I already said, is whenever we talk about a kernel, we are talking about a function that is executed on the device. And the only way to synchronize all the threads that we have inside the kernel, all the threads that we have running a kernel, is by terminating the kernel. It's the only way of doing global synchronization. As we will see today, it is possible to do synchronization, local synchronization inside a GPU core, inside a thread block, but the only way of doing the global synchronization is by terminating the kernel. And why is that? There are several reasons indeed. That the main reason is that, or one of the main reasons is that we want to write programs that can be used on any GPU. If you go to NVIDIA website or AMD website or Wikipedia or whatever, and you look for different models of GPUs, you will see that there are many different models, from very low-end to high-end devices, from, let's say, 2 GPU cores to 80 GPU cores. And we want to write our programs once, right? So the way that we write our programs is by saying, okay, I need to perform computation on these huge matrix, and I'm going to use 1,000 thread blocks. But now the way that these 1,000 thread blocks is going to be actually executed on the hardware will depend on what's the number of cores that we have, right? So we might have a kernel where we use 8 thread blocks, as we have here, and depending on our device, how powerful is our device, we will be able to do something like this, or we'll be able to do something like this, right? So here, for example, this is a device with 2 cores. That one is a device with 4 cores. The way that these blocks are scheduled onto the cores depends on the number of cores that we have. And actually, even though you can see in the slide that, okay, first we schedule 0 and 1, and then 2 and 3, and then 4 and 5, and then there is kind of the same. I mean, they are scheduled in order in this slide. We don't even have that certainty. We don't really know how they are scheduled. We cannot assume that block 0 is going to be scheduled before block 7. We cannot assume that, even though, yeah, it's true that typical internal scheduling of thread blocks is round robin. But, and that's actually something that I also mentioned the other day at the end of the presentation, but there is no guarantee that this is like that. So if we want to make sure that these 8 blocks have finished, the only way of doing this is terminating the kernel and then launching a new kernel. So if eventually we need threads in this block to use intermediate data produced by threads in this block, we will have to terminate the kernel and launch a new kernel with maybe, again, 8 new blocks. Okay? Yeah, going back very quickly to the previous slide, these are very common terms. Here you have, in blue, the CUDA term. In parentheses, you have the OpenCL term. They mean exactly the same thing. When we talk about grid, we talk about the whole number of blocks that run a kernel. And when we talk about a block, it's a certain number of threads that are going to run inside the same GPU core. Within a block, as you can see in the slide, these threads belonging to the same block can share data, exchange data or share data using an on-chip memory that is called shared memory, and they can also synchronize. So this is the local synchronization that I was talking about. And then, we have thread blocks or work items in the OpenCL model. Okay. About the memory hierarchy, this is kind of abstract view of the memory hierarchy. And actually, if you observe this, I mean, it's a nice picture, but it's kind of mixed thing, right? Because on the one hand, we have the memories, which is, let's say, something like hardware, like, for example, registers, shared memory, or the global memory, which is the DRAM. But then we also have like the software concepts, right? We have the entire grid, we have the block, and inside the block we have threads. But the slide is nice because it shows very clearly what are the different memory spaces that threads can access, right? So we have two, assuming, for example, blocks of only 2 threads. So we have these 2 threads. Each of them can access their own registers. Recall the pipeline register file where we have, the different SIMD lanes, and we have the whole register file that is partitioned, and part of this register file, certain number of registers, as many as they need, are assigned to the individual threads. From one thread, I can access my own registers, but in principle, I cannot access other threads' registers, but they can exchange data by using the shared memory, And all the threads running on the GPU can access data in DRAM, can access data in the global memory. The global memory is all these, or let's say the DRAM, the device memory, is all this orange thing here. But yeah, it's kind of divided into, from the programming perspective, can be divided into several parts. For example, constant memory is, the memory areas that you allocate for read-only data. Global memory is like the general purpose one for read-write. And then, if you want to use textures, which are, or surfaces, which are typically used in graphics programming, you can also allocate space for that, but it will be in the same device memory. Observe that this device memory can be accessed by the threads running inside the GPU, obviously, but also can be accessed by the host. And why is it necessary? Because we need to transfer input data from the host to the GPU and results from the GPU to the host. And more about the traditional program structure. Now we start, saying typical declarations and function prototypes and APIs. So we'll see this main function is going to run on the host, on the CPU. First thing to do, if we want to do computation on the GPU side, will be to allocate memory on the device using CUDA-malloc. You all are familiar with malloc. In CUDA, we have CUDA-malloc. The syntax in OpenCL is a little bit more complex, but in the end, we have the same kind of thing. Observe that in this CUDA-malloc, what we are doing is allocating a certain number of bytes, and we are going to use a pointer to access these bytes. And then we need to transfer data from the host to the device using this API, CUDA memcopy. This is the pointer to the CPU memory. This is the pointer to the GPU memory. And one of the things, you will see it in the next slide, one of the things that we are going to have here is the total size that we are transferring, of course, and also what's the direction of this transfer, because the API is the same for transferring from the CPU to the GPU and transferring from the GPU to the CPU. And then we need to set up the execution configuration, which essentially is how many threads do I need, how many blocks do I need. These are two numbers that we are usually going to determine based on what are the characteristics of the data structure that we need to operate on. For example, for matrix multiplication, the way that we typically map matrix multiplication onto the GPU is by assigning the output elements to threads. So, for example, if we have, we need to compute on a 1,000 times 1,000 matrix, this is my output matrix, what we typically do is assigning one thread per output element of the output matrix. So in this case, we would be talking about 1 million threads. And each of these threads is going to read one row of matrix A, one column of matrix B, perform the dot product, and store the result in the corresponding element of C, right? So what's the total number of threads that we need for this operation is 1 million, right? And now these 1 million threads need to be divided, needs to be grouped into thread blocks. right? You might recall that the other day I mentioned that typical thread block sizes are multiple of 32, right? So actually, typical numbers are something between 128 and 512. So for example, if you are using 512 and you have 1 million elements to compute on, what would you do? How many thread blocks you will need to launch? It's an easy calculation, right? But as you can see, the way that we write the program is, like as a function of the output size in this case. Next thing to do is to call the kernel. This is the kernel launch. Inside this this part, what we have is the execution configuration. So here we will have number of thread blocks that we launch. Here the number of threads, and then the arguments. What's going to be one of the arguments? Or for example, in our matrix computation, what would be the arguments? At least A, B, and C, right? We usually use, when doing GPU programming, D, we will typically use DA, DB, DC in order to distinguish them from the copies that we have on the CPU side, right? Those will be typically H. And next thing is when we finish the computation, the kernel terminates, and what we do is transferring the result from the device memory to the host memory. Now observe that the destination is this H out on the CPU side. The source is this D out on the device memory. And here we will also indicate that the transfer is from the GPU memory to the CPU memory. And we can repeat this as needed. It will depend, right? There are some algorithms that are iterative, typically, for example, graph processing. In graph processing, we go over the graph in multiple iterations, and for this of each iterations, we might be launching exactly the same kernel, or there might be also programs using multiple different kernels, and for each of the kernels, we will obviously have a different definition of the kernel, but in the end, what we are going to do is something similar, right? Okay, as you can see here on top, but also here as well, when we write a kernel, when we write a GPU function, we need to qualify it with this global, how is it called? A qualifier. To identify it and to distinguish it from a regular CPU function, like that float serial function that you have on top. And the way that usually, we are not going to enter the details of compilation and these things, but for you to know, when you write program, you will see that CUDA programming is very similar to C programming. Whenever you use automatic variables inside your program, these are going to be assigned, are going to be mapped into registers, typically. But we can also define shared memory, and essentially this is, we will need to use this special word inside the kernel function, inside the kernel code. We will declare like shared and then array of certain size in the same way as we do in C, for example. And inside one block, if we want to synchronize, we will use this. This is a local variable, is these sync threads. Okay, here you have like the exact definitions of all these APIs, CUDA malloc, CUDA main copy. Observe that this special word here, CUDA main copy host to device. This is the data transfer from the CPU to the GPU. If it's the other way around, it will be CUDA main copy device to host. And then for the allocation, we have CUDA free, and for explicit synchronization, we use this CUDA device synchronize. Why do we, this is not so important, but it's interesting also to mention. Why do we, or where are we going to need to use this CUDA, and where do we use it? We use this API in the host code. And where are we going to use it? Right after, typically, right after the kernel call, in order to make sure that the kernel has finished the execution. And why do we need to do that? Because it's the only way that we can make sure that the kernel terminated. Why is that? Because this kernel call is asynchronous, meaning that when the host code reaches this point, what the host is doing is calling the driver and the GPU driver and telling the GPU driver, hey, please start running this kernel on the GPU, right? But right after that, the CPU thread is free, so it can continue computing, doing whatever, like maybe arithmetic operations right after that. So if you eventually need to, to make sure that the kernel terminated, the specific API that you need to use is this CUDA device synchronize, right? Yeah, not always necessary, but it's good to know that it exists. It's, as you can see, it's not actually like these global barriers inside the GPU code that they actually don't exist in the bulk synchronous parallel programming model. Okay, let's start thinking about how do we need to map the computation inside our programs by having some running example here as image processing or simple processing on an image, which is a two-dimensional data structure. As you know, images have a certain height and a certain width. In this case, our beautiful image here is 8 times 8 of size. And as you know, when we want to refer to any of these pixels, what we typically do, as it is a two-dimensional data organization, what we do is image ji, being j the row and being I the column, right? So for example, this guy here is image 2.1, or this one is image 0.1, and this one is image 1.2. But how is this image mapped onto the memory? The way that this image is mapped in memory is in CUDA and in OpenCL, same as in C programming. It's a row major layout, meaning that the way that the entire image is stored in memory is as a linear array, and we store row by row, right? The distance between this element and this element is kind of a stride that actually has the same value as the width of the image, right? So whenever we are talking about image element ji, it's actually in memory image j times width plus I. You see, for example, this is image 0.1, so it's actually element 8 times, so 0 times 8 plus 1. Or this one, image 1.2. So if we want to access data, access this image inside the GPU code, inside the kernel, what we need to keep in mind is how this is actually stored in memory. The first, in this slide, the first way of doing it is by using one-dimensional grid. When we talk about the grid, it's the total number of thread blocks, recall, or total number of work groups, and this can be one-dimensional. When it's done one-dimensional, what it means is that our thread blocks have only one dimension, and we're going to have a certain number of threads inside this thread block. These are some, like built-in variables that we can use inside the, let me show it, okay, inside the, where is my cursor? Here. So inside the GPU code, we can use these built-in variables. This griddim.x is the number of thread blocks that the grid contains in the x dimension. This blockdim.x is the number of threads inside each thread block in the x dimension. And then for both blocks and threads, we have an index, right? So this block idx.x represents the index of the block. This is the index of the thread. So, for example, one way of distributing this whole image among blocks and threads is by assigning consecutive chunks of pixels to consecutive thread blocks. For example, we can assign these 4 pixels to block 0. Of course, this is a toy example. We will typically have much bigger images and much bigger blocks, but in this case, we consider that each of the blocks is composed by 4 threads. So, for example, these 4 pixels are these 4 pixels assigned to block 0, so this is, for example, the way that we are going to distribute these 4 pixels across the 4 threads, right? So whatever computation is related to this element will be done by thread 0. Anything related to this element will be done by thread 1, and so on. So now if we want to know which thread is, for example, accessing this or computing on this element, what we need to use is the block index, the block dimension, and the thread index. This guy here is the pixel number 25, and thread number 25 in the whole GPU is using it for computation. In this case, this would be thread block number 6. The size of the thread block is 4, and inside the thread block, so it's thread 1, which is going to work on it. So this is for an example for one-dimensional blocks, and this is for two-dimensional blocks, which is actually, like, let's say, more suitable for image processing, matrix processing, and so on, right? Because they are two-dimensional organization. It's also possible to use 3D grids and 3D blocks as well, but yeah, it's exactly the same thing here. So in this case, we have 2 dimensions of the grid in the X dimension, and in the Y dimension. Observe that in this particular case, grid dim X is 4, and grid dim Y is 4 as well. And inside each block, we also have block dim X is 2, block dim Y is 2, right? So the block that is going to operate on this tile of the image is, in this case, block 2-1. And we can assign threads to each of these individual pixels, and that guy, for example, would be thread index X1, thread index Y0. If we want to access a specific element in a specific row and column of the image, the expressions that we need to use are these ones. You see, block index Y times block dim Y plus thread index Y to determine what's the row here. I hope this is clear. If it's not, it will take you like 30 more seconds to look it yourself. Okay. Yeah. Okay, let's continue, and very brief review of the GPU architecture. Recall that we were saying, compare this GTX 258, 285 with the Volta V100. The number of GPU cores is different. The number of SIMD lanes inside each of the GPU cores is also different. Yeah, so this is an example. This is actually something like the internals of each of the cores of the GTX 285, for example, is something like this. You can see inside this one, what we have is 8 of these SPs, 8 of these SIMD lanes. So how do we need to do to execute one warp of 32 threads on top of these 8 guys? So we will do is we have 32 threads in each warp. When this instruction or this warp scheduler that we have here launches or issues a specific instruction for a specific warp, so we will first start the computation for 8 threads, then other 8 threads, 8 threads, and 8 threads. Every cycle, we can start computing for 8 threads, right? So this is corresponding to the old Tesla architecture that started in 2006 or so. And this is, you already saw this picture, this slide the other day. This is the NVIDIA Fermi architecture from 2010. In this case, observe that in total we have 32 of these SPs, 32 SIMD lanes, but actually the way that they are used is by using 16 on one side and 16 on the other side. Notice that we have two warp schedulers there, so we have two warp schedulers that are fetching instructions from the instruction cache, and they are issuing the instruction either on D16 or D16. So in this case, we need 2 cycles to start the computation for the whole warp. You see the difference, right? Actually, more modern GPUs, we directly have 32 of these. So in one single cycle, we can start the computation for them. Recall that thread blocks are mapped onto the GPU cores or streaming multiprocessors, and there they are divided into these warps of 32 threads, something like this. So whenever the warp scheduler fetches a new instruction, it's going to fetch an instruction that can actually be executed. There are no dependencies. If for whatever reason we need to wait until the previous instruction finishes to have one partial result as an input operand of the next instruction to fetch, this instruction won't be eligible. The warp scheduler internally uses a scoreboarding that is essentially like a table of the instructions that are ready for execution. And instructions that are ready for execution are those that have the operands ready, right? So this will be like the way of controlling the internal dependencies inside the GPU program. Okay, yeah, more terminology. I think that we have already gone through all this terminology, and here you have the comparison across the different NVIDIA generations. The latest one is Volta, that was released, I think, either end of 2018 or beginning of 2019, and yeah, I think that there's so it's, the last one is Turing. It's not in the slide. I think there's no Turing GPU with this many number of cores yet. Yeah, anyway, that's not so important. In the end, the architecture is still very similar to this Volta one, but you can see the whole evolution here and the nice choice of names for the different architectures, right? Okay, I think we are done with the basics. Do you have any questions so far? No? Everything is clear? That's great. And yeah, so I think that we can start with the performance considerations and maybe have a single break. Is that okay? Okay, good. Okay, so performance considerations. Yeah, as I said in the beginning, main bottlenecks of the GPUs. First of all, the data transfers between the CPU and the GPU. Second, the global memory access. In the end, this access in DRAM is where we have most of the, I mean, we're going to spend most of the execution cycles when we are doing GPU computing. For the CPU to GPU data transfers, we will see how we can deal with them or how we can try to optimize them. For the memory access, this is the first thing that we are going to talk about. Yeah, so we will first talk about what's the concept of occupancy, which is very important for the latency hiding mechanism that the GPU has. This latency hiding mechanism essentially is based on the fine-grained multi-threaded architecture that the GPU has. And then also an important consideration is how do we access to the memory. We need to have coalesced memory accesses. We will see what this means. And then we will also see how to use this shared memory that we have. Is an internal, actually it was in the, let me go very quickly back. So it's right here. It's this shared memory that actually maybe not in all GPUs, but it's typically the same memory space that the L1 cache as well, and is internal to the streaming processor or GPU core. So that's why all these units that we have here can access this shared memory. It's a scratchpad on chip memory. It's kind of software programmable cache. Its role is to be used as a cache, but it's something that the programmer can explicitly manage. It's not like a regular hardware cache where you just let the hardware work and don't have to worry about it. Here you can control it explicitly. Okay, so we will see how to use it. We will also go back to something that we actually started to discuss at the end of the lecture the other day, is the divergence inside a warp, how to deal with this. We will also talk about atomic operations, which is one of the sources of inefficiencies in the thread execution inside the GPU, because we need to have a serialized execution, especially in the cases where two threads that are running concurrently need to update using an atomic operation the same element in memory. And and finally, we will see what we can do for the data transfers. Okay, so let's start with the memory access. So as I said, GPUs are fine-grained multi-thread architectures. Here, the multiple threads are actually multiple warps. And what we do is that we can have warps executing, running on the cores, on the SIMD lanes, and these guys can somehow hide the latency of other long latency operations, like, for example, accesses to the global memory. So very naive toy example here. If you have, let's say, 4 active warps inside a GPU core, you can be running or executing instructions for the different warps. For example, instruction 3 for warp 0, instruction 2 for warp 2, and so on. And suddenly, warp 0 needs to execute this instruction 4, which is an access to global memory to read an entire cache line, for example. So so what we can do is, if we have enough warps running inside the GPU core, is we can continue executing instructions for other warps. Of course, for warp 0, we will likely have to stall until we get the values from DRAM, from the global memory, and then we can continue execution of instruction 5. So this instruction 5 will only be ready for issuing, eligible, as I said before, after this instruction 4 completes. Assuming that data that is read from memory by this instruction 4 is used as an operand by this instruction 5. But in the meantime, as you can see, we can hide this latency. And for that, in this particular toy example, we need 4 active warps. What might happen if we only have 2 active warps in this toy architecture is that at some point we have this instruction 4, and then, in the beginning, we can continue with the execution of instruction 3 for warp 1, but then instruction 1 also needs to access memory, so we will have all this gap that we cannot hide. So that's why it's important to have enough number of instructions ready for execution, because this way we can hide the long latencies. Problem here is that typical way of having this number of instructions ready for execution is having enough active warps inside the GPU core. The thing is that we cannot always have the maximum number of active warps inside the GPU core, right? Because there is obviously a limitation for the maximum number of warps inside the GPU core. Any idea what's this limitation? Don't think about any program. Just think about the architecture. Think about a fine-grained multi-threaded architecture. We can have up to a maximum number of warps. No, actually not, because instruction cache is not a problem, because all these warps are running the same program. So one of the things, if you review the slides that I showed you the other day, one of the things that determine what's the maximum number of threads in a generic fine-grained multi-thread architecture, or maximum number of warps in the GPU is the number of PCs that you have, the number of program counters that you have. Because as you can see, all these guys here, these 4 warps, are running the same program, but at a particular point in time, they are on a different instruction, right? So here is instruction 4 for warp 0, here is instruction 1 for warp 3. So each of them needs its own program counter. In the end, a program counter is a register, and we have a maximum number of registers inside, program counters inside the GPU core. So that's essentially what limits what's the maximum number of warps that we can have inside each of the GPU cores. But then there are more limitations, right? Because depending on the program, the number of resources, the different resources that these different warps need is different. That will depend on the program. We might have programs where we need, let's say, 2 registers per thread. That will depend on, how good our compiler is as well. But okay, let's say 2 registers per thread. So if we have warps of 32 threads, this means 64 registers per warp. But there are other programs where we might need 4 registers per thread. So in that case, is twice the number of registers that we need. And obviously, the total number of registers that we have inside the GPU core, the size of this register file, is also limited, right? And the same happens as well with the shared memory. The shared memory, this scratchpad memory inside the GPU core, has certain size, typically 64 kilobytes, and these 64 kilobytes need to be need to be partitioned and assigned to the different thread blocks that are going to be mapped onto the GPU core. You see, so these are typical values for the SM, for the GPU core resources. Maximum number of warps, 64, which is related to the maximum number of program counters. Maximum number of blocks per SM, it has also its own limitation, is 32. Register usage, the size of the register file is 256 kilobytes typically, and for the shared memory usage is 64 kilobytes. So, depending on what's the usage of these resources that each individual thread and each individual thread block does, we can have more or less thread blocks and warps running at the same time inside the GPU core, right? So now imagine, for your program, each thread block needs to use 30 kilobytes. How many blocks can you run inside the same SM? Only 2, right? So if I have 4 SMs in my GPU, I could be actually running 8 blocks at the same time. If my program, in the execution configuration, I launch 200 thread blocks, I can only have 8, and then 8, and then 8. For sure, the GPU has a very smart thread scheduler, and as soon as one of these thread blocks finishes, completes its execution, there is a free slot, and the thread scheduler is going to put there and start running a new block, right? And that's how it's going to work. Also observe that this occupancy, which essentially you had actually the definition in the previous slide, is the occupancy is like the percentage of active threads, active warps that we have. This occupancy for the same program might also change depending on what's the actual platform. Why is that? Because if you compare different generations of GPUs, you will see that these numbers have changed a little bit over time, typically increasing, right? That's for sure. Okay, so yeah, so these are the things that you have to take into account when you want to do the occupancy calculation. And in principle, one of the basic rules for optimizations of GPU programs is to try to increase the occupancy. in the end, it's not always like a very good practice. For example, if your workload is very, very memory bound, you have many, many accesses to global memory. It might be good to actually reduce the occupancy a little bit, because this way we won't put so much pressure on the interconnect and on the memory subsystem. But yeah, as let's say as an initial good practice for GPU optimization, increasing the occupancy tends to be a good thing. But in the end, it's a lot of exploration as well. Writing your program, trying different number of threads per block, trying different execution configurations, and play with these numbers quite a bit. Okay, second important consideration for the memory access is the memory coalescing. What does it exactly mean? Yeah, but this means that when accessing global memory, we should try to make sure that concurrent threads access nearby memory locations. That's, let's say, like the most basic definition of memory coalescing. And this is actually the way of achieving peak bandwidth, is when all threads inside a warp access one single cache line. Yeah, so the size of the cache line and the typical values of the cache line size in the L1 is 128 bytes. In L2 is 32 bytes. But if you think about, so what this means is that every time that L1 requests one cache line, it's actually 4 cache lines in L2. And actually, if you think about 128 bytes, what does it mean for a single warp? That means 4 bytes per thread, right? And 4 bytes is one single precision floating point or an integer, right? So that's like reasonable thing, right? Reasonable values. So what's a coalesced memory access? It will be something like this. So for example, I could write a program where I assign this entire row to thread 1 and I assign this entire row to thread 2, or I can write my program like that. I can assign this column to thread 1 and this column to thread 2. What's the difference between them? The difference is that when these two threads start the execution of the program, first thing to do is to read this element and this element. And if you look at these two elements, they are too far away. How much? Depending on this stride, this width of the matrix. So if this stride this matrix is very small, okay, that's okay. These two might be even in the same cache line, right? But if this is, I don't know, 2,000 elements, then for sure, thread 1 and thread 2 will be reading different cache lines. However, if I assign the computation in this way, thread 1 here, thread 2 here, these two elements are consecutive, so they belong to the same cache line, right? What's going to be the difference? The difference is that for the same access, here I need 2 memory transactions, while here I only need 1 memory transaction. So that's the way of doing the coalesced access and to have peak bandwidth in this memory access. This is a little bit more detail about what an uncoalesced memory access is. Imagine that I assign the rows to individual threads. So yeah, in this case, its matrix is only 4 times 4, but now imagine that it's 4,000 times 4,000. So when we talk here about time period, in reality, we want to talk about iteration. So in the first iteration, thread 1 reads this, thread 2 reads this, thread 3 reads this, and these 3 are very far away, different cache lines, so I need 4 memory transactions to satisfy this memory request, this first load instruction. In the second iteration, I access the next element, so this is again 4 memory transactions. Good thing is that, at least these days, GPUs have reasonable caches, reasonable size, so it's likely that in this second iteration, this thread 1 can directly fetch this from L1, right? But yeah, in the past this was worse, but still it's a very important performance consideration. And in the coalesced memory access, what I do is assigning threads to the columns in this case. So this way, in the first iteration, I have consecutive threads accessing consecutive elements. So in the same iteration, I only need to fetch maybe one cache line if this is a warp, let's say, and each of these is 4 bytes, so it's one single cache line. If it's double precision, it will be 2 cache lines, but are one after the other. Second iteration, and so on. And actually, you can see here what's the difference between. So it's important, right? Recall that slide talking about the disadvantages of SIMD processing, and one of the things that text says is that so you need to be smart when you organize data, when you arrange data inside memory to make it more SIMD friendly, let's say, and in this case is GPU friendly. And actually these are two different ways of organizing, in this case, an array of structures or a structure of arrays. The data is exactly the same, so we have two possibilities here. This is like, so this struct here contains 4 arrays. This is A, B, C, and D. And here what we have is that each of the, so in total this is an array of structures, and in each struct we have elements of A, B, C, and D, right? So if you think about this and you think about the typical program, what is more favorable, what is more desirable for GPUs? This thing, right? Because if I have multiple threads operating on this, I will have, in the beginning of my program, I want my threads to access elements of A, so I will have thread 0 here, 1, 2, 3, 4, and so on, right? So they are accessing consecutive memory locations belonging to the same cache line. While here, there is already a stride between these accesses, so more likely that I will need more memory transactions, right? And actually, you can see in the next slide a comparison of, accessing these kind of organizations. What we have changed here is the structure size, and this is for, this is like, so this could be like the array of structure. The longest, the structure size, I have more longer stride across threads. So you see how the throughput, how the the achieved bandwidth is going down very, very quickly, right? However, if you compare that to a CPU, it's kind of different. I mean, in the CPU, it looks like not so more irregular there, but you see that in general, CPUs are fine with having larger structures. And why is that? Because in CPUs, you typically have one single thread or maybe 2 threads or something like that. Each of them has its individual cache. So if I have my thread reading this element, I will bring all this data to the cache, and next I will have hits in the cache when accessing the rest of elements of the structure. Yeah, you can find more details about this kind of analysis in this paper. Okay, next thing, what time is it? Yeah, I think we can have a break, no? Let's have a 10-minute break. Is that okay? Okay. Any questions so far? Or any more questions? Okay. Okay, I think we can continue. Are you ready? Okay, next thing, data reuse. We are going to discuss now how to make use of this scratchpad memory, this shared memory that we have inside each of the GPU cores. Observe, for example, this image here and that green tile that we have there. So if you think, for example, about the typical filters that are applied in image processing, but not only in image processing, also in deep neural networks, these convolutional layers usually do something like that. We typically have a filter, and the filter is something like this Gauss thing. Is like like a small data structure, two-dimensional data structures with certain values, and we need to calculate the convolution for the pixel image, the image pixels that are, let's say, covered by this green window that represents the filter. So, yeah, the computation that we need to do for each of the individual pixels is going to be something like that. This is like the sequential code for this particular, in this case, is, as I said, called Gaussian filtering. So, but now if you think about what's the compute, so that's the thing. What we are doing here is accessing all these 9 elements here, and we take the 9 elements from the image, we take the 9 elements from the filter, and then we do the computation. But now if you think about what's the computation that needs to be applied for this pixel here, it's actually the same thing, but instead of being these 9 elements here, it's going to be with this window here, with this window of 9 elements here. So the thing is that there is a lot of reuse across the threads that are computing on these 2 pixels, right? In particular, out of the 9 elements, there are 6 of the elements that are shared. And that's the data reuse, and that's what we have to take advantage of. We don't want to go again to the global memory, which takes us several hundred cycles to fetch a cache line in order to do the computation. If we read this for thread 1, we want to reuse it quickly for thread 0, right? So what we do typically when we have this kind of computation, what we do is tiling, which essentially means that we divide the entire image, in this case, into pieces, chunks, tiles of a certain size, and each of these tiles is, in the GPU programming model, typically going to be assigned to one entire thread block. So now think about a thread block of 4 threads, two-dimensional thread block of 4 threads. Here, this is thread 0, 0, this is 0, 1, 1, 0, and 1, 1, computing on for the filter output for these 4 pixels. So these 4 threads will need to read all these values from DRAM and store them somewhere where they can be accessed much faster. And this somewhere is the shared memory, is the scratchpad memory. And this is something that the controller, so the programmer can control itself. For that, we will need to declare some array in the shared memory. In this case, is L data, local data of this size. And then we will have to synchronize. Why do we need to synchronize? We need to synchronize to make sure that we have finished loading the entire tile into the shared memory, and then we can run the computation directly reading the piece of the image, the tile of the image, from the shared memory, right? Again, back to the reason why we need to synchronize. It will be because typically this thread block is going to be composed by multiple warps. And as you know, the way that warps are scheduled is, independently of each other. So if I have, let's say, okay, let's assume in this example, let's assume that my warps have 2 threads. So here I have 2 warps, right? So these 2 warps need to go and read the entire thing. Warp 0 will be reading, for example, this part. Warp 1 will be reading this part. And the only way to know that both finished loading from global memory into the shared memory is by using this local barrier, these sync threads. That's why we need to use it. Okay? Yeah, so this is an example of using the shared memory. It's a typical case of usage of the shared memory. But the shared memory has also its own considerations, performance considerations. Why is that? Because the shared memory is a banked memory. It has multiple banks, typically 16 or 32, which actually is a number that is related to what's the warp size. So the perfect access to the shared memory by a warp, what is it? How is it determined? You already know how multi-banked or interleaved memories work, right? We want to avoid bank conflicts. We don't want to have two accesses to the same bank, because this way, what will happen is that the accesses are serialized. So if we have a warp of 32 threads, what's the ideal situation? We have each thread accessing each bank, right? So that's what we should try to have. Each bank can service one address per cycle. You already know that. Typically 32 banks, which is in line with or related to the number of threads in the warp. And the way that these addresses are mapped into the banks is something like this. 32 is the number of banks. We already saw this expression in the previous lecture. Okay, and this is interesting as well. Bank conflicts are only possible within a warp, right? Makes sense, right? Because the access to the shared memory is scheduled at a different time, that's for sure. So warp 0 and warp 1 cannot have conflicts. The actual conflicts happen inside the warp, among the threads that belong to the same warp. Some example patterns. Bank conflict 3. In this particular case, we have 16 threads, and we have 16 threads and 16 banks. If our stride is 1, we have linear addressing, then no bank conflicts. What's the access here? Let's say your array A with A0, A1, A2, A3, up to A16, for example. I have 16 threads, so thread 0 accesses A0, which is located in bank 0. Thread 1 accesses A1, which is located in bank 1, and so on. The width of these banks is 4 bytes, which also matches very well with the cache line size. You recall that, right? This is another example as well. We don't need to always have linear addressing. We can also have random addressing or different addressing. The only important thing is that all these 16 threads belonging to the same warp are accessing different banks each. This way, we will be able to exploit the maximum bandwidth of the shared memory. This is an example of n-way bank conflicts. For example, two-way bank conflicts. When does it happen? When we have a stride 2, for example, we have thread 0 accessing A0, thread 1 accessing A2, thread 3 accessing, so thread 2 accessing A4, and so on. This is what is going to happen when we write in our code A2 times thread ID. If we do that, then the stride is 2, right? And if the stride is 2, we are going to have two-way bank conflict. And think about that. We have 2 threads going to the same bank, which means that we are reducing the effective bandwidth by 2. And can be, of course, even worse. This is an 8-way bank conflict. So how can we reduce the shared memory bank conflicts? Of course, the layout is very important, right? But you know, in some cases, we might need to have thread 0 accessing element 0 and thread 1 accessing element 2. This might happen. Why is that? Because that's a computation that I need to carry out, or I want to carry out. So there are optimization techniques that we can apply. Being the simplest one, padding. Let me give you an example of padding here using the blackboard. If I can find what I need. Okay, so imagine that, you will see, it's actually very simple. Imagine that this is our shared memory, this is bank 0, this is bank 1, bank 2, and this is bank 31. So, I need my threads accessing something like this. a thread ID x dot x, which means that I'm going to have thread 0 accessing here, thread 1 accessing here, and so on, right? So what's going to be the problem here? The problem is that I have a two-way bank conflict. And why is that? Because I'm going to have one thread accessing here, which is which thread? Thread 16, right? So is this unavoidable? Of course it is, if we write the program that way, because we really need thread 16 access this element 32. And also, you know, these are the characteristics. This is the way that data is mapped. This is the way that data is, the addresses are mapped onto the banks, and this is the way that threads access the shared memory. Recall that the specific bank where one address is allocated is this, right? This address modulo 32. What can I do that? What can I do here? What is what padding means? Padding essentially means that I'm going to reserve extra memory locations for nothing, simply to avoid the bank conflict. What I could do is simply not use this and store A32 here. This would be A33 and so on. And in the next row, let's say, the padded position is going to be this one. So the good thing is that this thread 16, instead of accessing here, is going to access here in bank 1, where no one else is accessing, right? So I avoid the bank conflict, and now I have, I can get the maximum bandwidth from the shared memory. That's essentially the padding thing. Of course, this can also change. There might be other ways of doing it, but that's the main idea. Is it clear? Okay. Yeah, go down. Okay. Yeah, there have also been like different proposals to deal with bank conflicts as well. I think that I already mentioned this randomized mapping from this paper from Bob Rao in ISCA 2000, so in ISCA 1991, pseudo-randomly interleaved memory. So essentially the idea here is to use hash functions that do the mapping in a different way. Instead of having a linear mapping like address modulo 32, we can have like more complex addressing, and if this addressing is handled by the hardware, the overhead of it is negligible, and you can get a lot of performance improvement, and this is actually something like that, but specifically applied to GPUs. Yeah. So yeah, in general, actually, if you take a look at this work, you will see that the different functions that are being used here that are actually configured for the specific instructions, for the specific GPU programs, you will see that the impact that they have in the overall performance is really, really good. Problem of using these hash functions, problem of using these fancy addressing is that you as a programmer cannot reason very easily about what is happening. So because, you know, you may always have some, let's say, like corner cases where you really still detect, for example, when you do profiling of your program, you still detect that there are bank conflicts. But now you don't really know how the data is mapped onto the bank, so it's much more difficult to reason and try to solve it your way. Usually that won't happen so frequently, right? So yeah, but in the end, things like padding can be pretty useful in these cases. Okay, we are already done with the things related to memory access. We've talked about efficient access to global memory, trying to use coalesced memory accesses, efficient data reuse, taking advantage of the shared memory, and also what to keep in mind if we want to really have an efficient access to the shared memory. And now let's gonna talk about the pipeline itself, like about the SIMD utilization. The other day we already introduced the problem that we might have with the SPMD model. The good thing of the SPMD model is that I can write whatever I want. I can use control flow statements, for example, and I can have thread 0 going this way and thread 1 going this other way. You have a clear example here, branch and two different paths, A and B, depending on, for example, the value of data read from memory, or depending on the index of the specific thread, we will go through path A or path B. And the problem here is that this produces branch divergence, and branch divergence translate into warp divergence, intra-warp divergence. And why is that a problem? It's a problem because, the 32 threads of the warp are issued at the same time. So we have the warp scheduler, which fetches one instruction from the instruction cache, and then launches the 32 threads on the 8 SIMD lanes or 32 SIMD lanes or whatever number that we have. So they execute in lockstep. Ideally, they are going to be executing the entire instruction together over the whole pipeline, and that can be very efficient, as you can see the first instruction here in this picture. But if we have a branch, then part of them will go through one path, the other part will go through the other path, and the thing is that essentially we need twice the number of cycles to do the computation here, right? So can we avoid that? Well, the other day we saw a couple of proposals to deal with that from the hardware point of view, but unfortunately current GPUs still don't implement these fancy proposals. So what we can try to do is figure out how to write our programs in a nicer way to avoid these kind of programs. Let me give you a better example of, or let's say on code, what's an example of intra-warp divergence. Something like this, for example, we do some computation here. In principle, there is no divergence in this initial part, but then at some point we have this if-else statement, and now we want that, odd, so even threads do this and odd threads do that. This will be something like this in the execution. If I have wars with 32 threads, and these 32 threads are executing these compute instructions together, perfect, 100% utilization, that's fine. But then we want so even threads do this in the if part, the odd threads in the else part, right? So problem here is that half of the warp is unused here, the other half of the warp is unused here, right? Can we do something here? Okay, so this is a possibility. Divergence-free execution. I change the mapping of threads to the data. And now, instead of having, even threads doing this and odd threads doing that, now what I have is the 32 threads. I divide them, or in this case, consider that we have more than 2 warps, let's say, 64 threads, for example. What I'm going to do is that the computation that should be assigned to 64 threads is going to be divided into what was done by the even threads now is going to be done by the threads in the first warp, and what was done by the odd threads now is going to be done by the threads in the next warp. So something like this. When we reach the if-else statement, the if part is computed by these guys here, while the else part is computed by these guys here. And if these two parts belong to different warps, then I no longer have divergence, and I can have 100% SIMD utilization. This is obviously nothing, right? Because you don't know what is do this and do that. But now I'm going to give you an actual example that is a very nice one and very useful primitive in general in parallel computing is vector reduction. Vector reduction is that I have a vector, 12 elements in this case, and what I want to know is what's the total sum of these 12 elements. How can I do this? You might know that for vector reduction on a parallel machine, what we typically do is what is called a tree-based approach. Essentially, several steps, log n steps, being n the size of the array, and in each step, I have one thread adding up 2 elements. For example, in my naive mapping, I have thread 0 adding elements 0 and 1, thread 2 adding elements 2 and 3, thread 4 adding elements 4 and 5, and so on. This is naive, but it's the most straightforward way of doing it, right? I mean, of course, after this lecture, after these slides, you will always think on the right way of doing it if you have to program this or something similar to this on a GPU. But this is like the most straightforward way and the easiest way for a programmer to write this. The problem here is that as we make progress over the iterations, the number of threads gets reduced, which makes sense, obviously, because I don't have so many elements to add in each iteration. But observe that these threads are iteration after iteration farther away from each other. Actually, from the very beginning, I only have here thread 0 and thread 2 computing, and thread 1 and thread 3 are doing nothing. So even in the first iteration, I already have 50% SIMD utilization, right? So, and this is the naive mapping. Observe that this really simple program, right? So here I have a variable T that represents the thread index, and now over the iterations, I start increasing the stride, right? So here for thread 0, the stride between the 2 elements that needs to add is only 1. In the next iteration, the stride is 2. In the next iteration, the stride is 4. In the next iteration, the stride is 8. So that's what I have in this code here, right? I start increasing the stride from 1 until block dimension. Yeah, don't really worry about the limit for the end of the for loop for the example. But the point is that the stride is being doubled in every iteration, right? So if you are the thread that you have to be, then you perform this partial reduction. Problem, very low SIMD utilization. So how can I come up with a divergence-free mapping? Well, in the case of the reduction, is something really possible, because reduction typically is an associative operation, right? So think about the sum, think about the addition. I don't really care about, because of the associative property, associative and commutative properties, I don't really care about what's the order of the additions, right? I don't really have to add the first 0 and 1 and then 2 and 3 and so on. And so what I can do here is assign the input data to the threads in a different manner. And this way I can have consecutive threads working over the whole execution of the program. So for example, here to thread 0, I assign in the very first iteration elements 0 and 16, to thread 1 elements 1 and 17. And this way, One first benefit of this is, if you look at the memory access, is that for sure I'm going to have coalesced accesses. And second benefit from this is that I have consecutive threads working. So if this, instead of being 16, is 32 threads, the 32 threads belong to the same warp, right? In this example, you can maybe think about a thread block of 16 warps and think about warps of 4 threads. So if this is a thread block of 16 warps, I have the 4 warps working in the very beginning. In the next iteration, half of the warps retire, but the other half of the warps continue working. And inside each of these warps, so if this is one single warp, inside each of these warps, or in this particular warp, I have 100% utilization because all the threads of the warp are active. And then I continue, and so on. Yeah, in the very end, obviously, I don't have 100% utilization, but that's simply because the reduction is with less than, the rest of the reduction is with less than 32 elements. And yeah, if you look at the code, I will let you think about it yourself, but if you look at the code, this might be a little bit more difficult, complex, the addressing, but in the end, it's not that difficult, and yeah, so with this, I can achieve higher SIMD utilization. So it's a nice example of divergence free mapping. Any question? Okay, next thing, atomic operations. Recall atomic operations. I mentioned in the beginning, the problem with atomic operations is I have threads running concurrently, right? And if these threads inside the same warp need to update atomically the same memory location, I will have to serialize the accesses. Yeah, that's something that is going to happen for sure, but there might also ways of optimizing it. Yeah, so this is the syntax for an atomic operation in high-level CUDA programming language. Atomic add, where I have one element in memory. I have a pointer here, and in this memory position, I want to add this integer in this case. I mean, this is for, yeah, the syntax for integers, but they also work for floating point, double precision, and so on. Yeah, in CUDA, as you know, there is a compiler as well, and this compile takes your CUDA program and compiles it to the, you know, ones and zeros that the machine understands, right? But there is also an intermediate representation that is very useful, that is called PTX. And the reason why this PTX exists is because the architecture has changed over time, right? So, and you want to have the same program that you wrote 10 years ago should also work in 2019. So that is why there is a kind of intermediate representation or an intermediate layer in the compilation flow that is this called PTX. This is common for all GPUs, but then you can go to the specific assembly code that is called SAS for the different architectures. Actually, if you look at you read the PTX, you see that this is kind of simple to understand, right? So this is an atomic operation on shared memory. It's an atomic add on unsigned 32, 4 bytes, right? And this is the output. Typically, what this atomic add returns is the old value of this memory location. So this is the output register in register 25. This is the address in this RD14, the address in shared memory that we are updating, and this is the value that we are adding. So how does this translate to the SAS code, to the assembly code? That is the thing that is actually executed on the GPU hardware. Yeah, in the case, so it has been a change here. And that's actually something nice that shows how much, improvements in the hardware can impact the overall performance of programs. In the initial architectures, Tesla, Fermi, and Kepler, this atom share add what was compiled into this small loop. If you look at the loop, what you have here is a load instruction, then an addition, then a store instruction, and then a branch, right? And also, if you look at this, you can see that there are something here, these P0 and P1, which are predicate registers. You remember, we have talked about predicated execution, right? So essentially, this predicate register is one single bit per thread. That's enough, one single bit per thread. And what we are going to have here is 0 or 1, depending on the fact that the thread succeeded or not while trying to lock the access to the particular position, particular location in the global memory, in the shared memory in this case. So if we have two threads belonging to the same warp and they both want to update the same location, they have to contend for one lock. I don't need to say where these locks are. You can guess where they are inside the shared memory. So they contend, and only one of them can actually gain the access and lock the access to the specific memory location. And this gives us this predicate value. So if your predicate is 1, you will actually execute this and this. And if it's not, then you will jump and start from the beginning. The reason why they changed this is because this was very inefficient, right? Imagine, for example, you are, counting elements that are equal to 16 in a whole array. And you want to count, and the easiest way of counting, the fastest way of writing your code is saying, okay, let's use atomic operations. So I read from memory, is this equal to 16 or not? If it's equal to 16, then I update, right? I add 1 to this shared memory location. Yeah, so in the end, you have one single address that is being accessed by all the threads using atomic operations. So imagine that the 16 threads in the warp have read 16 from memory. So the 32 of them will have to go over this thing 32 times. So the number of instructions that you're executing here is very high, right? 4 times 32. NVIDIA improved the implementation of this. Since the Maxwell architecture, we have native atomic instructions in shared memory, and they are way more efficient, way faster. Yeah, this is a little bit more elaboration on the example that I just gave you, right? So in this case, we have these thread 0 and thread 1, which are going to, if they update different elements, and also in different banks, because of course, if this is shared memory, we also have bank conflicts when executing atomic operations. If they are, updating 2 different positions inside the same bank, we will still have bank conflicts. So we have these. If the access is something like that, then we clearly need an extra latency, serialized updates. And this is something that actually, I first gave you like a very naive example. Let's count how many elements are equal to 16. But this is actually like very typical thing that happens in some useful primitives, like, for example, histogram calculation. You might be familiar with histograms. They are used in many, many different applications, especially in image and video processing. And one way of assigning the computation of an histogram, let's say the typical way of assigning the computation of a histogram across threads is doing something like this. This is your input image. These are the different pixels, And yeah, I will typically have thread 0 reading this, thread 1 reading this, thread 2 reading this. Why is that? Because in the end, what I'm doing here is very little amount of computation. So most of the thing is going to be, most of the cycles are going to be spent on reading the image from the global memory. So I need to, you know, try to have efficient access to memory, peak bandwidth, codeless memory accesses, and if I want that, I will have to do this assignment. And now the thing is, if these guys here need to update this histogram in global memory, or maybe, yeah, in principle in global memory, I might have two of these inside the same warp updating the same bin of the histogram. So that's going to be an atomic conflict, right? And this entails serialization, and the performance of the program might go down very quickly. And this is very frequent in histogram computation of natural images. Why is that? Because these pixels here is very likely that they have the same value, right? So for example, these threads are reading all these pixels, and these two are reading pixels with value 192. And the distance between these two pixels is 2. So for sure they're going to, or very likely going to belong to the same warp. Right? So this will entail the serialization. So one way of dealing with all the possible conflicts that we have when updating, when generating this histogram is doing a very simple but effective technique that is called privatization. The example that I'm giving you here is a very naive thing, is for histogram calculation, but this privatization is also, for example, applied to graph processing when you follow what is called a top-down approach. I don't know how familiar you are with graph processing. I don't really need to explain so much about that, but you know, in graph processing there are essentially two ways of doing graph processing. One way is doing top-down, and the other way is doing bottom-up. The difference is that you know that graph processing algorithms are typically iterative, so you go over the graph. Let's say, in principle, the way to be faster is by doing a top-down approach, in which you only need to, in each iteration, you only need to worry about the frontier, meaning the vertices or the nodes of the graph that you need to visit in this particular iteration, right? The other approach is bottom-up. Bottom-up means that you're always checking all the vertices of the graph. And what you try to do is say, okay, I've been assigned this vertex. Am I in the frontier or not? If I'm not in the frontier, I don't do anything. If I'm in the frontier, I do something. Problem is, if I have, I don't know, a graph of 100 million elements, I will need 100 million threads, and many of them will be idle most of the time. Why is that? Because they are not in the frontier. Right? So that's the problem of a bottom-up. In theory, it's more desirable to have a top-down approach in which I make progress and I only have threads exploring the nodes in the frontier. But the problem here is that this frontier will be typically a queue, and if I want to enqueue a new vertex into the frontier, I will have to update some global shared, or I mean, when I say global or shared, what I mean is an atomic variable that I need to update so that I get a new index to enqueue in the queue. This is only an example of usage of atomic operations and privatization, because if I map this top-down approach to a GPU, I could have privatization, like small queues assigned to each of the thread blocks, such that each thread block only needs to update its own queue, and at the very end of the kernel, I will merge all the small queues. So this is privatization, and this is what we can also do for histogram computation. Instead of having one single histogram for all the thread blocks that I'm going to run, one single histogram in a global memory, I can have multiple subhistograms of the same size, as you see in this case, like 4 bins of the same size in the different shared memories, in the different SMs. And when I'm done with creating these subhistograms, I merge them into a final histogram in global memory. And this is a reduction. Recall the reduction. You already know how to do very efficient reduction, right? What we have seen before. Yeah, so this is a way of dealing with, alleviating what's the cost of these atomic operations. Any question? Okay. Next thing, data transfers between CPU and GPU. Recall that this is one of the main overheads that we have in GPU computation, one of the main bottlenecks. Why is that? Because typically in the traditional accelerator model, we have the CPU, we have the GPU, in the middle we have a PCI Express, or, NVLink can reach up to, I think, 25 gigabytes per second, but this is clearly one order of magnitude lower than accessing the global memory. So the problem here is that if I need to, I need to compute on a matrix of 4K times 4K, I will have to move a lot of megabytes from the CPU memory to the GPU memory, and this takes time, right? And depending on how much computation I'm going to perform on the GPU side, I will be able to amortize this cost of the data transfer or not. So, so there are, let's say, some ways of trying to deal with this. There is the possibility of using asynchronous transfers and what are called streams in CUDA or command queues in OpenCL. And these are defined as sequences of operations that are performed in order. I will show you what we mean with that. In principle, as you know, we need to transfer from CPU to the GPU, then do the kernel execution, then do the transfer of the results from the GPU to the CPU. So usually it's going to be the default stream is going to be something like this. These two are two sequences, so are two operations that belong to the same string because they are performed in order, right? I cannot start the execution of the kernel until I have finished copying the data from the CPU memory to the GPU memory, right? So if this is, matrix multiplication, first thing to do is to transfer both matrices from the CPU to the GPU memory, and then I can start the execution. So these two operations represent a single stream, the default stream. The good thing is that in some cases, the data that I'm transferring in this part of the transfer is going to be computed in an independent way of the data that I'm going to transfer in the rest of this time. So the good thing is that as I have transferred, for example, some rows of matrix A and some columns of matrix B, let's say, because I was giving you the example of the matrix multiplication, I could actually start the computation of these dot products and start computing some of the elements, right? So what we can do is divide in the computation into multiple streams such that they are independent. These two are one stream, they are in order, you see, but independent of this stream, and this stream. As soon as I'm done with this transfer, I can start the computation, and at the same time, because these two operations can be asynchronous, these two streams can be asynchronous, I can overlap the data transfer for the next chunk of the computation with the actual computation of the first chunk. And by doing that, I can save a lot of time. For sure, this is something that I cannot always do. I need to know my computation, I need to know my program, I need to know if I can do it or not, but it's not so strange, right, that you can do it. For example, these are just like some estimates of how much I can save, right? So if I have n streams and execution time of the kernel is longer than the the time for the transfer, what I would be hiding is the transfer, right? So the only thing that I will see here is this. This is TT over N streams is this piece here. And then what I see next is this TE, right? And this is the other way around in case the transfers are dominant. I don't know why this happens, but yeah, I guess that you get the point. Obviously, from doing this, from dividing the computation in multiple streams, there is a little overhead of managing of the this thing, but yeah, in principle, it's really worth trying. And as I said, it will depend on the specific computation, but yeah, for example, video processing, this is very, very good use case for this overlapping of communication and computation. You have a sequence of frames here, so if you need to compute on the frames individually on each of the frames of the video, you will need to transfer the entire video and then compute, but if you do this stream processing or stream execution, you can transfer a chunk of frames, and while you are computing on this chunk of frames, you can transfer the next chunk of frames, and you save all this amount of time. Okay? Clear? Good thing is that over time, well, yeah, you see this is from 2012. Over time, this has improved, and these days, NVIDIA provides something that is called OpenCL as well. Both CUDA and OpenCL provides something that is called the unified memory. And actually, with this unified memory, the GPU can request pages by itself to the CPU memory. And this is transparently handled by the driver. So you don't really need to, I mean, of course, it has a little bit more overhead that you could control yourself if you do it manually. But yeah, these transfers can now be, or this overlapping can these days be achieved in a completely transparent way. Yeah, and this is the summary of what we have seen so far. Is that okay? Shall we continue? 20 more minutes? Okay, let's talk about collaborative computing. Are these new features, they, let's say, started to be available in CUDA maybe 2 or 3 years ago. And what they enable us is to have like a tighter collaboration between the CPU and the GPU. Or if we talk about OpenCL, a tighter collaboration between the CPU and other devices, which could be 2 GPUs or 1 GPU and 1 FPGA, or multiple combinations like that. We can very first review what we have just seen. Actually, this is like a typical program. Notice that we have here CUDA malloc. So we have first malloc for the input array in the host, CUDA malloc for the input array in the device. Then we transfer from the host to the device, and then we allocate the output, and then we launch the kernel. We have this CUDA device synchronize. Recall that this is the way that we can make sure that that this kernel has finished before we do something else. In principle, typically we don't use this thing. If the structure of the program is like that, we don't use this thing because this CUDA main copy is synchronous in the way that it will never happen before the execution of the kernel. But there is also one CUDA main copy async, which is the one that we have to use for the CUDA streams. And in that case, this and this will be asynchronous. So if we really want to make sure that this finished, then we need to use this. Okay, a small clarification that you don't really need. But yeah, so what's the problem that we have here? The problem that we have here is that the actual collaboration between CPU and GPU is very difficult. And when I'm saying actual collaboration, or when I talk about collaborative execution, I'm talking about the CPU and the GPU using their threads to compute, indeed, to do actual work. Because if you look at this model, what we are doing is simply the CPU thread, the only thing that it's doing is offloading the computation to the GPU and waiting for the GPU to finish, right? So during all this time, the CPU thread is doing nothing. The GPU cores are doing nothing, at least related to the CPU cores, sorry, are doing nothing at least related to this program. I could somehow try to get benefit or use these CPU threads by, for example, writing some computation here, right? I could, I don't know, like a very naive thing. Imagine that I need to do one vector addition. And my array, my input array has, or my two input arrays have 1 million elements. And I know that the GPU is much more powerful for parallel computation than the CPU, but the CPU can also do some of the work, right? So I could say, okay, 1 million elements, let's assign 100,000 elements to the CPU, to the GPU, and the rest to the CPU. So what I could do is launch this GPU kernel for this input of 100,000 elements, and the remaining 100,000 elements are going to be added here. I could do that, yes, for sure. But it's like a very, I don't know, naive way of doing this collaborative execution, right? And yeah, that's fine. That is still fine in a vector addition. Why is that? Because I can clearly partition what is assigned to the CPU and what is assigned to the GPU. There's no overlap, right? But now imagine that, I don't know, I have a more complex computation where, for example, a histogram calculation. I have the entire image, and I could say, okay, this small number of pixels to the CPU, this large number of pixels to the GPU. But now the problem is that they both need to update the same histogram, right? So yeah, that's probably not doable, at least with one single histogram, that's for sure. So yeah, to deal with these kind of cases, yeah, we have this unified memory. I'm going to use the CUDA term, which is unified memory. In OpenCL, this also exists, and it's called shared virtual memory, but it's exactly the same thing. This unified memory was introduced in CUDA 6 for the Kepler architecture, but by that time, it was simply like kind of wrapper that simply was like doing the data transfers for you, but there was no actual unified memory with CUDA 8 and the Pascal architecture starting, this was actually 2016, end of 2016. Yeah, so these two can access at the same time the same arrays, right? And the thing is that you only need to allocate once in the CPU memory, and somehow the GPU can directly access the CPU memory. Somehow means that every time that the GPU needs to access the CPU memory, sends a page request, like a page fault. Come on, this guy is independent. Okay, so every time that the GPU needs to read something from the CPU memory, sends a page fault to the CPU, and this page, 4 kilobytes, typically, I think it's 4 kilobytes, are going to be transferred from the CPU memory to the GPU memory in a transparent manner. And it can also happen the other way around. It's memory coherent, meaning that if the GPU takes these 4 kilobytes, modifies them, and after that the CPU needs to update whatever in these 4 kilobytes, they will be transferred back to the CPU memory. As you can guess, this has obviously an overhead, but it's also a huge jump in terms of programmability. Yeah, so this was the, yeah, so in the beginning with the good thing of using the unified memory is that now you don't need to do the double allocation that we had. We actually have this malloc here, but we don't really need this because this CUDA malloc manage. Observe that now the API changed a little bit the name. This CUDA malloc manage is actually allocating in both places at the same time for you. And that's why we are using here simply a mem copy. And we don't have an actual CUDA mem copy. There is no actual explicit transfer between the CPU and the GPU memory. And yeah, and this is an example of what I told you before. In the traditional model, if you want to partition these vectors and do some computation on the CPU, yeah, the CPU can do something here, right? Can do some things here, but it's not actual fine-grained collaboration. The good thing is that with the unified memory, the way that it's already exists in Pascal, Volta architectures from NVIDIA, but also on the HSA architecture from AMD and other vendors, is that, you see, the kernel is launched with these arguments, output and input arrays, and as soon as I launch the kernel, and this is a completely asynchronous operation, the CPU can continue computing and can directly operate on these arrays that are also being operated by the GPU kernel. And this is transparently handled. All the memory coherence here is transparently handled. So these are the APIs, CUDA malloc manage that you have already seen, and it's also possible to have system-wide atomic. So now it would be possible to have one single histogram that is being updated by the GPU threads and the CPU threads, for example, like using this fetch add on the CPU side. On the GPU side, you would need to use this atomic add system. It's a kind of atomic add, but it's over the entire unified memory. That's why it's different from the atomic add that we have seen before for the shared memory, which also has the same syntax for the global memory. This is in OpenCL 2.0, or since OpenCL 2.0, and this is C++ AMP, which is a related thing a little bit. I don't know if you have heard about this. Yeah, it's kind of C++ high-level programming model. As in the end, it ends up compiling to OpenCL typically, and from there to the actual assembly code. And with these collaborative patterns, we can. And with these features, we are now able to implement these collaborative patterns. So this is what we originally have in a traditional accelerator model. In the traditional program structure, we have different, for example, two kernels, right? This is the computation that we need to carry out, right? This is kernel 1, this is kernel 2. And what we have in the middle is this coarse grain synchronization that is, it's simply the kernel termination and launch of a new kernel. Recall that this is the only way of doing synchronization, global synchronization inside the GPU, right? So this is like the program structure. We have the entire operations that we need to do here can be divided into multiple tasks. You can, for example, think about each of these tasks being assigned to a single thread. And actually inside these tasks, we can have subtasks. I don't know, for example, adding two values and then reducing the partial results, for example. Those could be the two subtasks here. So with the new features, it is possible to these new programming features, it is possible to do a very efficient partitioning across different devices. In this case, device 1 and device 2 can be one CPU and one GPU. And you know, because these are different devices, they are better for some tasks and are better and worse for other tasks. For example, in this particular case, the yellow subtask runs faster on device 1, and the green one runs faster on device 2, right? So yeah, this is one possible partitioning that I can do, right? And I would have my coarse grain synchronization, the kernel termination, and then I continue. And also you can see that, yeah, this thing is faster on device 1, this thing is faster on device 2. Right? And what I'm doing here is I'm simply assigning to each device an amount of computation that is related to the compute power that I have in the different devices. Maybe I have 4 CPU cores, and here I have 80 GPU cores. So yeah, okay, I will assign many more of these tasks to the GPU threads, right, than to the CPU threads. This could be like the most naive way of partitioning the data. But now observe that, okay, I clearly see that some operations are faster on the CPU, while other operations are faster on the GPU. So what I could do, actually, if I look at this, I can first look at the entire task, right? Those tasks there are faster. Each individual task is faster on the GPU, while here, each individual task is faster on the CPU. So one thing I can do is some sort of coarse-grained task partitioning where I run all this computation in device 2 and all this computation on device 1, right? I could do that. And in principle, you see that in this picture, you don't see any concurrency, right? You don't see device 1 and device 2 operating at the same time, right? But I could really do that because, for example, if I'm operating on a whole video stream that is composed by thousands or hundreds of thousands of frames, I could be here, I could be doing this computation for the previous chunk of video frames. So I can have this concurrency. But it could be even nicer if I do a fine-grained task partitioning, and this is something that is really doable these days with all these new programming features. I directly assign those subtasks that are faster to the device where they are faster. So the yellow thing in device 1, the green thing in device 2, and then at some point I need to do a coarse-grain synchronization, and then the light green thing on the CPU, the dark green thing on the GPU, and so on. And this communication, this synchronization, can be implemented how? Who can give me an idea of how to do this? Maybe very late. For example, using a flag, right? When this, I assign this to thread 0 in the CPU, for example. And when thread 0 is done with this, sets a flag in the unified memory. And on the GPU side, I have, for example, a GPU thread block checking that flag using atomic operations. That's possible, this atomic add system that I just showed you. So this guy updates with an atomic operation the flag, and this guy here sees that this flag has been set, and now this data is ready to start the execution on the GPU side. And as you can see, this can be very flexible, right? Because I can have CPU threads and GPU threads continuously running and communicating using these new features like the system-wide atomics, and which at the same time take advantage of the memory coherence across both memories. And that's more or less the idea here of these collaborative patterns. This is like a very naive example. I mean, I think that I already mentioned this example. This is a histogram calculation for an image. So I assign part of the image. This would be like the traditional thing. In the traditional thing, I need to assign part of the image to the CPU, part of the image to the GPU. Each of them has its own subhistogram, and finally I need to merge them or reduce them. This can be fine, but it's a little bit more complex to program. It could be even much easier, actually, if they both share the same histogram in the unified memory, and threads from these SMs and from these CPU cores directly update this histogram. Don't ask me if this is efficient or not. As you can guess, for a single histogram of, let's say, 256 bins is not efficient, but from the programming point of view, is actually very, very good. And actually, one more thing is that this is not efficient on discrete GPUs. Why is that? Because you have the PCI Express bus in the middle, right? So if you need these threads here, updating this, you will have to move one page from the CPU memory to the GPU memory, and then back when you want these threads to update this, right? So you're going to have like this ping-ponging that is going to destroy your performance. But if you have an integrated GPU, and these two things are inside the same chip, and this is the same memory space, is the same DRAM, then it's going to be much more efficient. And you can see quite a few of examples of this collaborative implementation. Bezier surfaces, it's a kind of processing for, for graphics. This is on an NVIDIA Jetson. I don't know if you have heard about this platform. It's like a board that contains a CPU and a GPU, CPU with 4 cores, 4 ARM cores, and a GPU with 2 SMs. So this is the 17% of speed up that you can get from doing a collaborative execution. Here you have, this is also performance improvement on an AMD Kaveri, which is an integrated system on chip with 4 CPU cores and 8 GPU compute units or GPU cores in AMD terminology. And here it's 47% improvement over the GPU-only version. Here you have a few more examples, padding. I want to go over these. You can see some results showing some performance improvement. This is another thing, string compaction. In this case, how much? 82% improvement on this AMD Kaveri over the GPU-only implementation. What else do we have? And this is breadth first search. Actually, the way that this is explained, and I cannot elaborate because we don't have time, but you can take a look by yourself. This is the top-down approach that I talked about before. And, this applies several tricks, like not only privatization, but also persistent thread blocks, which is also a nice way of optimizing GPU programs. I'm going to explain you this very quickly. So remember that from the beginning, I told you have this whole array. This whole array has 1 million elements. You're going to use thread blocks of 128 threads. So what you do is, how many thread blocks do I need to launch? This much, right? 1 million divided 128. Or the ceiling of that, right? And this is the number of blocks that I have to launch. But in the end, these, 100,000 thread blocks are going to be scheduled like, for example, first 4, and then when one of these finishes, 1 more goes here, and then the next one goes here, and so on. So the idea of using persistent thread blocks is that I only launch. It's a little bit more complex to program, but in the end, it's kind of a very easy thing to understand. Instead of launching, let's say, 1,000 thread blocks, what I launch is only 4 thread blocks, and what I have is these 4 thread blocks to go over the whole array. So when thread block 0 finishes with this part of the computation, instead of retiring and finishing and releasing this slot for the next thread block, what it does is go into this part here and compute this part here. And now, good thing of doing this is that, for example, I can control the computation in a better way. By doing a scheme like that, I know exactly where this guy is working on, where this guy is working on, and it might be possible to synchronize them. So it could be a way of doing this global synchronization that is not possible if you don't deploy these persistent thread blocks. But as I said, this is like a little bit more advanced programming, let's say. Yeah, you have more performance here, some results for the integrated thing. In this case, graph processing, breadth first search for this graph of New York roads is like 15% performance improvement. Some sample code. It's a related thing, single source, shortest path on the AMD Kaveri, 22% performance improvement. More examples, and this is the thing that I wanted to show you. If you want to take a look at these kind of collaborative patterns, you can access this Chai benchmark suite where you will find many of these patterns and different ways of using these new programming features. And that's all for now. I hope that you found it interesting. Thank you very much for your attention.